This is problem number 8 from the sample test problems for test number 1. Consider the graph of y equals cosine x given below. A, sketch a rough graph of its derivative below. Let's see if we can get both of these on the screen at the same time. Okay, so first thing I'll do is grab the points that are critical points or turning points on this original graph. So I see one down here, up at the top it turns, down at the bottom it turns. It's just turning over there, and actually, even in the very beginning, it feels like it probably came from a turn over there. And then I will draw a little tangent line at each of these points. And the reason I like to grab the turning points, the critical points, is that the tangent line is horizontal. And so if I'm thinking about graphing the derivative down here below, the things that I'm going to graph are going to be of the form x, comma, slope of the tangent line. And so let's go ahead and start grabbing some of these points. Keep them in red for the derivative. So the x-coordinate of this first point at the bottom, well, you're supposed to know the cosine curve well enough to know that that x-coordinate is exactly pi, comma, and then we're graphing the x and then the slope. And the slope of that green tangent line is 0. And then we'll go up to this point here at the top. The x-coordinate of that point is 2 pi. And again, the slope is 0. This one down here, 3 pi, and then the slope of that tangent line is 0. Up there is 4 pi, comma 0. And then the very first x is 0, and the slope of that tangent line also 0. So what we're going to do is we're going to plot these points straight down here in this new graph. So 0, 0 is there. Pi, comma 0 is directly below the point that's up there at the top. And the next one is 2 pi, comma 0. And then 3 pi, comma 0. And then finally 4 pi, comma 0. So again, to figure out where I'm supposed to put these points, I'm just going straight down from the x's that we had before. I guess we kind of missed on that one. We'll fix that. Okay, next thing we're going to do is pick a few points, a few representative points on this original curve. And we'll just maybe pick one in each interval. So for example, you could pick this one here, and maybe that one there, and pick that one, and then maybe this one up here. And then again, we'll draw a little green tangent line at each of these points. So that's got some downhill slope, that's an uphill, that's a downhill, that's an uphill. And I'm not going to go ahead and write down the coordinates of any of these, but I'll just say that there's some x for this point. I'm not even going to guess what it is. And then what kind of a slope does that green tangent line have? It's got a negative slope. So it's going to be the x and then a negative number. And then at this point right here, it's that x, whatever it is, maybe it's 4.5, and then a positive number. So something comma positive. And then at the next point right here, that's some x and then a negative slope. And then finally some x over here and a positive slope. So all we're going to do is we're going to drop these points down. So we said this one was some negative slope, so it's down here someplace. And there's a point down there that's on the derivative. And then the next point we said was here, and it's some positive number, so I'll stop up there at some positive slope. And then we keep going. Next point over here is something negative, so we'll go down here and plot some negative number. Again, if you really wanted to be more precise than I'm being here, you could find the slopes of those tangent lines or estimate those slopes anyway by just counting boxes. Find the slope by finding 2 points that are on each of those green tangent lines. And it looks like we have one more, and this is some positive number, so we'll stop up here. And then all we're going to do is connect the dots. So it looks like this derivative goes down. Now, it doesn't necessarily hit there and turn around. It could actually hit there and then keep going down a little more. I didn't necessarily pick the bottom point, but anyway, that's we're just approximating here, so it looks like that. Then it goes up, hits that point. Maybe that's the top, maybe it's not. It's the next x-intercept. It's this point, and this point. And that's the graph of our derivative function. Again, there's lots of latitude in terms of getting full credit for a question like this. Part B, use the end derivative function on your calculator to generate a graph of the derivative function. How does it compare to the graph you drew in part A? Okay, so before we even do the commands, we're really hoping that what the calculator says looks an awful lot like what our estimate was up here. So there are a few different ways to graph this. I'll just do one of them here. We're going to use the nderiv command. So that's inside of math. You can just hit 8 right now, that's where it is, or if you want to scroll down until you find nderiv, you find it there. So either hit 8 or scroll down and hit enter. So the syntax for this nderiv command is you type in the function. So the function in this case, the original function, is y equals cosine x. So we'll just type cosine x. Close the parentheses that the calculator inserted for you on this x. Then we type a comma. This is part of the syntax for nderiv. Then you tell it the variable is x. Then you put a comma. And then normally you'd put a number here. You'd say, I want the derivative at x equals 5. And you just put a number. But I don't want just the derivative at 5. I want it at every single point. And the way you tell the calculator to give you the derivative everywhere is to put another x. Then we close the parentheses. And I'm going to graph the function, but I just want to say two things first. Number one, check your mode. Make sure you're in radian mode. Almost all of calculus is done in radian mode. If you put degrees, your graph will not look like this. So get that calculator in radian mode for any trig question in our class. And then the other thing I want to do is fix the window. Negative 10 to 10 isn't maybe the best window for the cosine graph. So let's get the graph to look like the one that's drawn here. So it looks like it goes from 0 to, I don't know, maybe 13. And then in terms of the y's, looks like -1 to 1. So we'll graph that. And so before we hit graph, again, we're hoping it looks like that. That's our best guess anyway. So we said it started at the origin, then went down, and then up to the top someplace, and then there's the x-intercept, down to the bottom, next x-intercept, up at the top, and then we stopped it right there. I typed in 13, so it went a little bit further on this graph. So that's looking pretty good. Okay, so I went a little crazy with my screenshots here, but just wanted to let you folks have an image of everything that I put into the calculator. And so answering the second part of part B here, it says, how does it compare to the graph you drew in part A? And so the idea here is that it's very close. So we're happy about that. And then finally, part C, what function do you think you drew in part A? At this point, we actually don't know exactly what the derivative of cosine x is, but gosh, this one down here sure looks like another trig function. It looks like a sine or a cosine. You can answer in any number of ways here, but I'll just put a guess here. Maybe something like f prime of x equals with a question mark. So to me, this looks like a sine curve because I like my sine curves to start right there at the origin, which is where this one goes. So I could say maybe this is a sine curve. But normally sine x starts at the origin and then goes up before coming back down. This one starts off going down. And so it feels like maybe it's not sine x, but perhaps negative sine x. Certainly you could say that it's a cosine graph shifted horizontally, but for me, I think it's easier not to do that horizontal shift.